model was run to predict BMI, which is it was listed here. We're told it's a continuous variable, which means, right, it is linear regression we're looking at, not logistic regression, which we'll start today. The study variables were female, yes or no, and describing the one's weight for themselves as either as underweight, normal weight, combined one category, or overweight or obese. So we have 3 different groupings of self-described weight. Interpret the outputs and be sure to include the regression equation. So we have the table. We have the different variables, right? So describe self as obese or overweight. That means when we have a categorical variable, right, when we run the regression, we leave out the reference group. Right? The reference group isn't explicitly in the model, it's in there implicitly. The reference group here, right, would be describing self as underweight or normal weight. That's why it's not there. And these things are all going to have, these variables have to be interpreted relative to the reference group. And then female, yes or no, and it is here. In the outputs, this column, the unstandardized coefficients, right? These are the coefficients we're going to be concentrating on for interpretation. We'll also want to look at the p-values to see about significance. The confidence intervals one could also talk about, but it's not going to be as necessary if you've covered the bases on everything else. So over here, in terms of output, I do have the regression equation at the end, but people describe themselves as obese. So looking at this variable, we want to take it one variable at a time. When we talk about the variables for interpretation, we want to be talking about is in the coefficient, there's 2 different aspects. There's the magnitude and the direction, right? How big or small it is, and how that translates to impact on the outcome, and what direction is the impact. Then we want to look at the p-value, right? To see, we want to also look at, is it a significant association, or is it not, or is there a trend towards significance? That's the other part. So we really got 3 parts for each variable. The magnitude of the coefficient, the direction of the coefficient, and the p-value. That's what we want to make sure those elements are in here. When we describe the coefficient, right, we also have to, for categorical variables, we better make sure that we state clearly that that effect is as compared to the reference group. Now, when you have a 0-1 variable, right, really it's like the reference group is just the 0 for that, right? So we know that if this is the impact of being female, that would mean, of course, as opposed to being male, that would be the 0 here. When you have categorical variables, the 0 is the ones who are 0 in all the other categories. So if your 0s both here and here, then that must mean you're in the underweight, normal weight category. So let's take a look. Describing oneself as obese or very overweight. The coefficient 15.466. So we're saying that people who describe themselves as being obese have a mean BMI, right? Because whenever we're talking about the impact, we're talking about the impact on the outcome. You're talking about an impact on the mean outcome. We understand that any individual one isn't going to be exactly that, right? That we're saying on average, people who describe themselves as obese have a mean, right, BMI that's 15.466 higher than for those who describe their weight as either, and that's our reference group, who describe themselves as underweight or normal weight. So compared to those describing themselves as underweight or normal weight, the ones who describe themselves as obese have a mean BMI that's much higher, right? Quite a lot higher, 15.466. Right? And the effect is statistically significant. The p-value right here is 0, so right, quite small. So it is a statistically significant effect. That's how we interpret that variable. Questions on that one? Okay. Next, people describe themselves as just overweight. They have we look at the coefficient there, 6.196. So for them, their mean BMI is about 6.196 higher, right, because the coefficient is positive, than for the reference group where the people describe their weight as underweight or normal weight. When we look at the p-value for this one, right, come over to the significance column, we get 0.028. So 0.028 is small, right? So we're used to looking at less than 0.05 as being significant. So we say that is a statistically significant effect. Yes?
I have a question about how you would interpret the intercept, the constant 19.624 in this.
Okay. That will come in when we talk about the regression equation. So we'll get to that. Okay? Shortly. So you won't be in suspense too long. Okay. Now, when it comes to sex, females, right, has a coefficient negative 3.137, but we also see that the p-value is 0.073. So we often talk about p-values between 0.05 and 0.1 as being a trend toward significance. Some people will refer to it as marginally significant, right? It's something where there's still a fair amount of evidence to suggest that the alternative is true, but you're not quite at the point where we feel really comfortable saying, yeah, this is beyond reasonable doubt. So because the p-value is between that 0.05 and 0.1, let's say there was a trend towards females having a lower mean BMI because the coefficient's negative, so they tend to have lower BMIs, and on average about 3.137 lower than males. Now here, right, first of all, if you say females, I don't really need you to have to say as compared to males. If you say it, that's wonderful, right? But it's kind of obvious if you talk about females, you must be comparing them to males, okay? So whenever you have a 0-1 variable like that, it's quite obvious, what you're comparing to. Any questions about these parts?
Because whenever it's been above 0.05, I've just said it's not significant.
Right. So I would encourage you to be a little more broad and really look at that 0.05 to 0.1 as being a trend toward or marginally significant. Now, sometimes it depends also like on your data sets. If you're working with massive data, like I'm looking at the Medicare data set and I have this enormous data set. So if it's between 0.05 and 0.1 and you have this enormous data set, then you kind of figure, it's not much. If there's really an effect, it must be incredibly small if this large data set couldn't manage to get it to be fully significant. But in a lot of studies, the 0.05 to 0.1 may also include, may be a situation where the sample size may not have been real big, or you didn't have a lot of people who had that characteristic, so you'd be a little bit concerned. And it's good to be able to communicate that it is, not far off. Let's remember that 0.05, right, is an arbitrary magic number. Right? There is no inherent scientific reason why 0.05 has to be the cut point. Right? So this has become the traditional cut point, and we feel that it characterizes things as being a reasonable approach. But what's the real difference between having a p-value of 0.049 and 0.051? Right? They're really both borderline significant. Right? So you do want to think about the p-values when they're not quite 0.05.
So if it was above 0.01 or 0.1?
Once it gets already above 0.1, people tend to just say it's not significant.
Do you include that in the equation?
Depends what you're doing. I would say, when you're talking about, if you have a regression equation, then technically, significant or not, it's part of that equation. And those values were calculated based on those variables everything was based on those variables being present. If you want to be able to say, here's a model for people to use in the future, then we may say, let's take out the variables that aren't significant, rerun the analysis, and say, if you're only using this set of variables, this is what you should do. Okay? Okay, yeah, Jordan.
So for this quiz, if you said that was not statistically significant, that would be correct.
If you said it was not statistically significant, right, I would say that's not correct. So, right. So I think, yeah. So on that one, there were, yeah, I would just say, Zoe, to say not significant instead of trend, I would only take a half point. Okay. Yeah.
I was confused on how to describe that. I feel like there's not a association, but it's showing it as a trend. So
That's fine.
Is that correct?
Yeah, I mean, you're still saying it didn't fully meet the standards of significance, but you're also still indicating that there was a trend towards it. So that's good. Yep.
So just a different point.
For this part, he said if you said it's not significant, that would be a half point off. Yeah. So.
So here's the question. When you just say, so when you're looking at literature and it says there's a trend, does that always mean that it's not statistically significant? It's not a statistically significant association, but there seems to be some sort of pattern, or can a trend refer to something that is statistically significant?
Now, well, if we're going to say, okay, I mean, people may be able to use the word trend differently and say, you know, there was a trend of increasing, it trended towards increasing numbers with something else, but it depends if they're referring specifically to the statistical significance. I mean, you can use the word trend also to describe like a slope and say, look, here we see a trend towards increasing values, so it, you know, over time or something. So you have to be careful with that. But when referencing these statistical significance, if you say a trend, we're really generally talking about that 0.05 to 0.1. So, yeah. So sometimes, you know, if you have a study and your p-value is a little just beyond the, you know, just above 0.05, so people may try to increase, see if they can increase the sample size a little more, get some more observations, and see if they can, you know, bring that down. So, Matt?
Are there any other words like trend that we should be conscious of?
Like I said, some people will say marginally significant to describe that range. Borderline significant, especially if it's really close to 0.05, borderline significant would be appropriate also.
Because I just was remembering back to some of the earlier notes, and even, I think it was marginally significant.
Right.
Okay.
Yeah, that's right.
Just, what about referring to it as not being able to reject the null hypothesis? Is this something where you could say you can't reject the null hypothesis, or that you would tend not to, or do you just avoid that?
Well, we're saying we have not presented a strong enough case to confidently reject the null hypothesis. But the fact that we see it's in that range suggests that, you know, we're not so confident saying that we shouldn't reject it. That it's in that, you know, it's a little bit more indeterminate, and we're, you know, it should, you know, it requires further investigation. So, okay, any other questions? Yes.
You said that we should, even if that p-value for being female were greater than 0.1, that we would still include it in the regression equation. Would it be better to just rerun the analysis and take, like, if the p-value is really high, should we just rerun the analysis and take that out as a variable to get a more accurate line? Because it seems like it would be affecting, like it shows the effect, because it's showing that there's an effect on BMI.
Right.
You know?
There is, anytime you have a variable in the model, even if it has absolutely no effect in reality, right? But it's a sample, everything's randomness, you know, it's going to maybe look like there is, it's not going to be perfectly no association in it, right? Statistically, there won't be any, you know, you may have a super high p-value, but the numbers aren't going to work out, so there's exactly no relationship, right? So everything that goes in there, it affects things like a little bit in the model. There are two schools of thought. There is a school of thought that says variables that aren't significant you should remove from the equation. If they're really not significant, then they're falsely taking some effect out of the model. In health, we generally don't do that. We generally go with the idea that we create an a priori model that's with careful selection and thought based on literature, and we test that model. In the end, if something doesn't seem to be significant, we also have to recognize that if there's a really, really tiny effect, there could still be a really tiny effect, but if it's a really tiny effect, you'd need an extraordinary sample size to be able to detect that with confidence. So it could be that it's there. On the other hand, if you're trying to find associations, so people don't usually will just leave the model as it is. We're still going to get the coefficients we need, and if it really doesn't have any impact on the model, taking it out won't really change the other coefficients by anything meaningful. When it's going to be used for prediction, right, when this gets back to what Troy was saying before, if you're going to say, here's a model for you to use in practice for prediction, so then you're probably going to want that model to be simpler and get rid of variables that don't seem to be contributing. Then in that case, I would rerun it just for this. Okay, good. Any other questions? Okay. Yeah.
Break it down individually to individual sections like the.
Oh, I'm sorry. I didn't. That's what I skipped right over that. The equation. Closed up shop too soon. Okay. The regression equation, right? You put all the pieces together, right? You just take that column of coefficients and put it in. The constant means there is no variable associated with it. It's a fixed value. So that's that coefficient. And then for each variable in the model, we have the coefficient. Positive for these two variables and negative for the female variable. So there you subtract. Now you've got an equation which is saying that on average, if you take somebody with characteristics as, say, 0, 1 here, 0, 1 here, 0, 1 for female, you plug them in, we can come up with what a mean BMI would be. So we need that constant in the model if you're trying to do any kind of prediction or talk about the output, because this is going to change the outcome. Regardless of the constant, the meaning of the coefficient here is the same. This is the difference that if you make this variable increase by 1, in this case go from 0 to 1, if a person describes himself as obese as opposed to normal weight, we say on average it increases the BMI by 15.466. That's totally independent of the constant. But if you want to come up with an actual predicted BMI based on those characteristics, you better include this value or you're going to be off by 19.634. So to get the mean BMI for a person who describes them, let's say it's a female describing herself as overweight. So to estimate their BMI, we would take the constant plus the 6.196 because this variable is 1. We'd skip over this because the variable would be 0. And then here, female would be 1, so we'd have to subtract off the 3.317. So in order to come up with what our predicted or what our best estimate is of a mean BMI for certain characteristics of patients, we have to have that whole equation, and that includes the constant. Well, if you could take the people in your population with different characteristics and see how they do compared to what actually was observed. But yet, with this as a model, now you can say, what is the mean BMI for women who describe themselves as overweight? And you could just plug in the characteristic. Female is true, that's a 1. Describe yourself as overweight, that's a 1. Describe yourself as obese, that's a 0. So for somebody with those characteristics, this equation tells us what the mean BMI is. And then we can do it for all the other groups as well. I have an idea.
As you're looking at the different, if you're looking at a type of person in your population, you swap that out.
Yeah.
Okay.
So we need those roving cameras. So what she asks is, so then if you want to look at different people, kinds of people with different characteristics, what you have to do is, right, swap out the values. Instead of being 0, 1, 1, you have to swap it to match whatever group you're looking at. If you're looking at obese males, then you have to plug in a 1 over here for obese, a 0 here for overweight, and a 0 here for female, and then you could calculate the mean BMI for an obese male.
So for a normal weight male, would you have to take out one of these and use it as a reference? Or
So if it's a normal weight, right, as the reference, that means these two are both zeros. So for a normal weight person, it's this, 19.634, right, minus that over there. Now, if you look at those actual numbers, there should be something that should make sense to you, should be clicking in here. So according to this, the women would have a mean BMI of females at 16.317 or something, right? Tells you it's probably not an adult population. Okay, these are kids. I don't remember if this was from my middle school data that I was using or something. So, all right, so you got some big differences there. There was a hand somewhere. Yeah.
So for a normal weight male, would it be
Exactly. So meaning the constant here, right? The constant is always, that's the outcome when everything else is 0. And in this case, a normal weight, a male who views themselves as being normal weight, doesn't mean they are, right? Those men would have those males had a mean BMI of 19.634. Exactly.
you would get that even if you switch the reference group and the dummy variables?
Well, if you switch the reference group, things are going to shift so that you still end up with the same things, right? So if you made overweight as the reference group, this coefficient will change to this minus this, the difference compared to that group, right? And the normal weight would then be negative that. So, yeah, so changing which one the reference group is shifts the values because it's all relative to a reference group, but it doesn't actually change your predictions for anybody. There was another one of those strange burping sounds coming again. I really don't know where that's coming from there, but okay. Anybody ever read The Plant That Ate Dirty Socks? Who said yes? Someone.
I don't remember it, but I remember reading it.
Oh, it's great. It's hysterical. And that one, then the plants eat the socks and then they burp. But anyway, it is a very fun book, The Plant That Ate Dirty Socks, but we will not actually cover that. That will not be on the next quiz, which is in 2 weeks. So some years ago, a student sent me along this cartoon from whatever those 4 letters are, XQCD or whatever, QXC. What is it?
I think it's XKCD.
XKCD? Oh, that sounds good. What is this? I don't know. I never saw what it was supposed to stand for. But anyway, so whatever the 4-letter comic is. Let's see. There you go. So I thought that was pretty good. So decided to share that. Okay, so now there might be another. I don't know if there's another one talking about a trend towards being a statistically significant other. A few things to go over. Interim reports. References does not mean bibliography. Bibliography is you just list all these sources that you checked at some point. References means that in the body of the paper, when you're citing something and that comes from a specific source, you cite what that source is. That's the reference for that statement, for that where you are in the paper. I want references, not bibliographies. Okay, so the interim report 2, which we had before, is supposed to include the analytic plan, table, descriptive statistics, and certainly by interim report 3, we want to have those nice tables. I'm not asking for outputs in the interim report. Yeah, I think I say it somewhere in one of the documents and the details of the reports, maybe on the final report outline, which is in the syllabus, where it gives the details. But I'm okay doing it either the numeric sequential listing and then having the references numbered at the end, which is true in most clinical-oriented journals and a little bit more in the a little more common in public health journals, or the more social science approach of you put in parentheses the author and year. See, it did it again. Do you hear this? It's not my imagination, right? Okay. So you put the author's names in the year of the publication in parentheses, and at the end, you have all your references then in alphabetical order. I'm really okay with either, as long as you keep to a consistent format and everything is indeed cited properly, and it's not incredibly difficult for me to find the right reference to match, figure out which one it is that matches with it, then I'm okay. Okay to have one hypothesis with the bivariable analysis. For the most part, we're doing regressions, but there may be a couple students who have a situation where the bivariable analysis really is of special importance and needs to be one of the hypotheses. But you also have to have adjusted analyses, regressions, which I think pretty much everybody was doing. You should be, at this point, finishing up all the recodings based on the feedback. You kind of really need that because the next interim report, you're supposed to have your descriptive statistics and bivariable analyses. You kind of need to have the variables recoded properly to get there. Don't wait too long. If you haven't done it, please get moving on it, because if you do it, and that's when you start running this, in case you find some unpleasant surprise and something's not working right, like it'd be nice to find that out before you're ready to turn it in. Review each proposed analysis. What subset of people are you using? So make sure you define that for each problem. That gets into like the inclusion-exclusion criteria. Just what are the rules for who's included in your analysis? If it's people over a certain age, if it's I'm excluding people who have a certain diagnosis, whatever that is, just make sure you state that very explicitly for each analysis. Let's see, next week, actually, I don't think that's next week when we create the subsets in class. I think that's going to be in 2 weeks. Also, a reminder, the last official class is December 2nd. December 9th technically is a reading day, no class, and December 16th, the week after, is our day for our presentations. So December 9th, if you don't come, I don't shoot anybody. But it's an optional class, so it's up to you. But since it's a time that you've all blocked off in your schedules as to generally be available, it's a particularly good time to have a lab session, in effect. So come with your laptops, and I may review a couple of points, answer questions, and then Zoe and I will be here to support you. So that way, by then you should be like really ready to run your regressions and do it, or doing your last subsetting and finally running the analyses. So you have a chance to do it with supervision and be able to get some help. I'll try and set up some other hours when I'm going to be available. I create other hours. When I create lab hours, what that means is I set aside blocks of time during which you're top priority and you have full powers to interrupt. With that, so I'll be in the office, my office, and if you're nearby working on it, anytime you have a question, you come. I try to keep those hours relatively unscheduled, but if anybody who needed to see me, they're warned. Any student comes in with a question, I interrupt, they get priority, and then we get back to it. So there will be some time for that so that you can get some additional support aside from the regular TA hours. So outcome variable is your dependent variable, right? It's kind of people often think of as like the result. And we're saying it's a result of the independent variables. The independent variables are your study variables and your adjusters, right? They're all independent variables, and so when running the regression, they all get thrown together in the same window in SPSS. Again, study variables, those are the ones you're trying to study. Those are the ones you're interested in and you'll make inferences about. Adjusters are there just to remove potential bias, and we don't comment on them other than to say our analyses were adjusted for. We will include them in the table 1 where we describe the sample, because that's still part of describing what the group. So the only difference between a study variable and adjusted variable is what you do in interpretation, how you handle it in communicating the results, right? You communicate the results, or an adjuster, you don't, right? Julia.
So when we run like a regression, you don't want those appended as like kind of as outputs. You want the data from those regressions to be turned into tables and then put into our report.
Right, and we're going to see how the table should look like for your outputs. So I'm going to give examples. Okay, linear versus logistic. We are going to talk about logistic regression today. It all depends on the outcome variable. If your outcome variable is continuous, it's a linear regression. If it's dichotomous, use a logistic regression. It has nothing to do with the nature of the independent variables. The independent variables, study variables, adjusted variables, doesn't matter whether it's continuous, dichotomous, categorical, none of it matters. It can all be accommodated regardless of whether it's a linear or logistic regression. If it's continuous or dichotomous, you just put the variable in. If it's categorical, we talked about making a series of dummy variables, the 0, 1 dummy variables, and leaving the reference group out. That's all handled the same whether it's linear or logistic. So the independent side, it doesn't matter the nature of the variables. Okay, we've really spent a lot of time talking about those things. So risk adjustment, we're trying to take bias because it may be that there's additional risk in one of your study groups or at higher values of your study variable. So we're concerned that it may be a bias in the analysis, right? It only is truly an issue if two conditions apply. If some other variable is both associated with the outcome, so it does affect the outcome, and if it's also correlated with the study variable. Because even if it affects your outcome, if it has no association with your study variable, that means there was no bias. But a priori, we often don't know that will be the case. So if one is true, we think the variable is associated with the outcome variable, then we adjust because there's potential for bias. And that's where we just say, what are the usual predictors of that outcome? We want to make sure we adjust for those. If 2 is suspected, that we think it may be associated with the study variable, then as long as it's even possible that it could be associated with the outcome, we'll be safe and you adjust. If it turned out both were true, it's associated with both the outcome and the study variable, then we know there's definite bias. And if you didn't include it, your numbers are definitely going to be wrong. One thing we've only made allusions to, but we haven't actually dealt with, was overfitting the model. If you can imagine, if you have 5 data points and you say, but you have 10 variables, that's not going to cut it, right? You're trying to use all this predictive ability, and you only have 5 observations. This is not going to work. So the problem is that as you add more and more variables, if your data set isn't big enough to be able to support that analysis, then the model becomes unreliable, and the confidence intervals get really, really big. So as the confidence intervals get really big, it makes it really hard to find significant results. But it may simply be because you have too many variables in the model, there really was an effect. So that's a big concern.
When you say independent, you mean adjusted variables?
No, independent variables are study variables or adjusted variables.
Can you have too many adjusted variables?
Yeah, all this is too many independent variables. When it comes to running the analysis, there's no difference between adjusters and study variables. It's only in how you talk about the results after. So all these issues we're going to talk about in modeling, if it applies equally to study variables and adjuster variables. Linear regression. So in linear regression, we try to have at least 15 observations per independent variable. That's a general rule of thumb. Some try to push it up to 20, that at least whenever possible to try to get it to there. And for exploratory purposes, people will often settle for 10 because when doing exploratory analysis, often you're only working with pilot data, and you're not expecting to make the definitive conclusions. You're really trying to do is learn enough to know what should then be studied more extensively. So for exploratory purposes, 10 may be fine. So you need to be able to check this when you're running regressions. do you have enough observations for the number of variables you have in the model? The number of independent variables, remember, that's for everything that shows up in that equation. If you've got a 4-level categorical variable, we know we're going to make 3 dummy variables to include in the model. That counts as 3 variables. So while it's 1 categorical variable, for the regression analysis, that's 3 independent variables. All 3 count in making that assessment. It's very important. So let's look at this and think about it for a minute. Don't blurt out the answer. So you take a chance to look and try to tell me how many independent variables are there for this model. So think about it for a minute. Okay, I mean business now. Okay, Rana, take a stab at it. How many independent variables do you think we have in this model?
5. We'll put age, height, sex.
And what? Okay, well this is just defining the population. So you see we have smoker, if it's yes, no, and we see it's dichotomous. So it is yes, no, so that's 1. Age, we defined it as being continuous. So that only counts as 1. If it was categorical, right, then it would count as more variables. This is why, one reason why sometimes you'll find people will choose to code age as continuous in situations with limited data, because otherwise it's going to count for a bunch more variables, and there may be other important variables that you won't be able to include in the analysis. So 1, 2, 3, 4. All of these are continuous or dichotomous, so they all count once. So that's good. Okay, now change it to now age is categorical, all right? So Justin, can you tell me now how many variables do you think, how many independent variables are there? Great, 6. So we have the 3 from before that didn't change, dichotomous, continuous, dichotomous. Age has 4 categories, but we don't include the reference in the regression analysis, right? We don't include that in the model. So that's 3 more variables. So we have 6 independent variables. Great. Now looking at this, right, and this is from the FEV data set, right? So how many independent variables can this data set support? Now think about it. Think about how you would do it, even if you don't get the calculation worked out.
What do you mean you don't include the reference for the age categories? What word do you?
Well, when you have a categorical variable, right, we make dummy variables for each level, but we leave out, when we run the regression, we don't include the reference group.
What would be the reference group for?
Whichever one you decide is a reference group. But whatever one it is, it's one of those variables, it's out. So it doesn't change the number of variables, and that's all I wanted to focus on, not which variables was reference. So, okay. Sheena, do you feel brave today?
No, I can't.
Okay, that seemed to be a very clear answer of no. So Latasha, before you get to run off, so I'm going to call on you now. Do you have an idea how we can figure that out?
Something with the total that's on
Okay, what's the total here?
174.
Right, good. So we have 174 observations. And we said was, the basic rule of thumb, if it's going to be 15 observations per independent variable. So we take the 174, divide by 15, and you'd see what you get. If you're doing an exploratory analysis really done as more pilot work, then you might settle for 10. If you're submitting this for an NIH grant proposal, you'll probably shoot for 20. But using rule 15, you get about 11, which would have been enough for the model we wanted, with an interaction term if we want. Okay, now let's look at it again. How many independent variables? So now, I think Sheena can feel more brave. So I'm going to give her a chance to redeem herself and tell me how many independent variables do you see here?
There's 7.
7. So there's 4 variables listed, and every one is continuous or dichotomous. So every one counts as 1. So there would be 7 here. Okay, example of overfitting. Let's say you had the same analytic plan, but using a randomly selected subset of 22 observations. Well, we had 7 independent variables. So really, we should need 7 times 15 or 105 observations. Or if we're just doing exploratory work, we might settle for 70 observations. But we only had 22. And 22 divided by 15, you only get 1.5, right? So you only enough for like 1 to 2 independent variables. So with 22 observations, you can't do much with it, right? What do you have? 1 or 2 variables. Very limited. If you have a 4-level categorical variable, you can't even do it, right? Okay. So here, that's pleasant. 1 second. So I'm just saying, so a regression analysis is running a regression analysis, and main thing I want to do is show you the difference. So I created the other one said 174, but I think there was somebody missing for that variable or something must have been. Oh, this is a different data set, right? This is, all right, this is the case lower class mental health study. This is with a full set of data, and above it, it's the same analysis, but I randomly selected 22 observations. Okay, this actually, SPSS can randomly select a subset for you. So I had to do it, and I ran the analyses just to see how things might differ. Right? Now, okay, so if we look at them, if you look at the variables and look at the p-values, look at the differences. So like minority, right? Not only the coefficient's very different, the p-values way different. Let's look at some others. Sometimes you can also get a fluke because you only have 22 variables, right? So you could get something that just happened to, work out kind of extreme. You can get that too. But in general, a lot of times you're going to find, like in a lot of these variables, you're going to find a lot of things that are the p-values end up being, smaller here, tighter confidence intervals when you have more data. But you also hope to get, in general, just better estimates, even better point estimates, because you're not as subject to flukes in small data sets. Jordan, did you have your hand up? Okay, great. That's because I could sense what your question was. Okay, variable selection methods. So what happens when you find that you don't have enough observations for all the variables that you wanted to include in the model? Now what do you do? Okay, ideally what happens is, right, we a priori define the model that we think is appropriate, and then we try to incorporate a study design that will accommodate testing all those variables. But when this is not an option, then one option is that's really popular in some of the social sciences and is used by others when necessary, though we're not big fans of it, is stepwise regression. Stepwise, you're going to do everything one step at a time to see about making changes in the model. We'll start at one point and then consider the pool of candidate variables that you were considering. So it would just take that whole list of independent variables, those combination of study variables and adjusters, and then consider them one at a time. Forward regression means you start with a null model. You start with nothing in it. You look at all the variables, check the model. What would it be like if each of those variables was included, but just one of them at a time, and see which variable has the biggest impact or which was the most significant. And it'll say, okay, we'll add in that variable. Then we'll run the model again, and we'll check every possible other variable, see which one would add the most by adding it to the model, and do that one. And then you have rules for when to include them or when not, when to get rid of variables. And so there's stopping rules. And it will go through this process until it comes to the stop where there's no other variable to add to the model that meets the criteria for entering a model, and none of my variables are leaving because of my rules for when a variable gets kicked out because it's very not significant, then you come to an end and you say that's your model. So using these approaches usually ends up removing a bunch of variables, and then you don't usually have the problem anymore with the number of variables in the model. You can get different results if you start with a forward than a backwards. If you start with the backwards, you start with everything in it, and you work your way down. You're not guaranteed to come up with the same model as starting with nothing and working your way up. You're also not guaranteed you're going to come up with the absolute best fit model. That's one of the problems with it. You know, it does get you to something. It is a reasonable procedure to go about, but it doesn't mean you end up with the absolute best model. Stepwise, really in truth, the formal definitions of forward and backward, forward mean you only add variables, and backward would mean you start with everything and you can only take out variables. And true stepwise would mean you can both either add or remove. In SPSS, it really always does stepwise. What it calls forward and backward is the starting point. Do you start with nothing and start adding, or do you start with all the variables and start subtracting? But either way, you can add variables or take them out. And then they give ranges with p-values. Like they give you 3 different statistics you can use. They all work well. In terms of p-values, I usually use like 0.05 to 0.2. Because I don't want to throw out model variables just because they just miss by a little bit. They're not quite significant. And I want to see what variables are in there. And usually, if I have a defined a priori model, I have reason to believe all those things are of potential value. So I'd like to have as many of those variables in there often as possible. If you're trying to come up with a simple predictive model, you may start off and do a forward regression and say, I want to have the simplest model I can, because when it comes time to predictive models, if they have a lot of variables, people don't use it. Just reality. So stepwise regression is one way we can reduce the size of the model. It performs lots and lots and lots and lots of tests, right? Because every time you're checking every variable that's not in the model to put in, every variable in the model to pull out. And if you're going to keep running gazillions of analyses, it's potentially running into an issue with, well, you're running so many tests, you're bound to have some fluke results included. Okay. So here are the rules I tend to use, about the 0.05 to 0.2. And there is a separate rule. There's one rule for what you need to enter into the model and another one to go out. So actually, I'm sorry. Actually, when I run it, I tend to use, I'll just use 0.2 period and let them come in or go out, whatever. Changing those rules depends also on just how restrictive you need to be. If you've got a large pool of candidates and not many variables can be included, then you may set up very much stricter criteria for getting into the model. If you only need to eliminate a few from a large set of variables, you can be very liberal in your criteria for entering the model, okay. I'm not sure why I said this here unless it's in the homework, but now, oh, that's right. You just use it. So if you've got your laptops with you, we will use the case lowerclassmen mental health data, and we'll step through this. Trying to get set up, and again, today we're going to go till 3 o'clock, but it means we're not going to have a break because we're ending so early. So, okay, so if we open up the case data, so we want to do linear regressions. So, so we'll just go to linear regression like we've done before. Analyze regression linear, and let's. Now this is from. See, I think they may have it labeled the stepwise part. I'm not sure if it's labeled differently in this New Year's version. So you'll have to tell me. But the dependent variable, we put the PHQ score, and then put those 5 variables as independent variables, and then we're going to want to go to the method. We want to be able to run a stepwise regression. Because I seem to remember in the new version, it just has like forward or backward, and then 3 variations of forward and backward. So is that what you're getting? Anybody up to that point? Okay. So I'll give you a little bit of time to catch up. How many people are at the linear regression screen? All right, we're getting some people there. If you click on method, there is one option is just enter, which means just put all the variables in and run the variable, running the exact model that you asked it to run, right? Then, does it have like 3 forwards and 3 backwards, right? So all these are stepwise regressions. So in the previous, we used to have stepwise was different than forward and backward, and now I believe the forwards and the backwards are all stepwise. They're just a question of where they start. Start with a null model or start with the full model with all the variables in there. So just pick whichever one you want. Okay, we can do, one second, let me just see. So let's do a forward regression, okay? Pick one of the ones. The criteria they use are all valid. Pick the forward regression with one of the 3. And then we're going to need to click on options. The option is going to be where we can tell it the criteria, the rules for what's the rule, the threshold for entering the model, what's the threshold for exiting the model.
So we're not doing stepwise, we're doing forward?
It really is stepwise. And the new one, what they're calling forward is a stepwise regression that begins as a forward regression. So it starts with no variables in the model and looks what's the first one to enter. The backward regression starts with all the variables and starts examining about taking out, but it does allow for forward and backward movement.
So the default is enter, and if it's enter, then nothing happens. But what happens if you click on remove? Does it take out any stepwise regression?
Where are you looking at enter and remove?
Method, I have enter, stepwise, remove, backward, forward.
You have enter, remove.
Yeah.
What else?
And stepwise, backward, and forward.
Enter, remove, backward. Yeah. Oh, so you have stepwise and backward and forward? Oh, I thought when I was running mine, I didn't see. You have a Mac. You have a Mac.
I was PC.
PC, it has it.
PC, and you have
The same thing, enter,
Eh,
stepwise, remove.
enter, stepwise, remove,
Backward, forward.
backward, forward. Okay. So we're looking at stepwise. Okay. I thought backward and forward. Maybe have it reversed. Maybe this was an older version. But it's one of the versions I remember as being a little different. But okay. So let's run the stepwise, right? That's because that's what I'm doing here. In practice, I would be more likely to run a backwards regression when I can, because I want to get as close to my original hypothesized model as possible. And then click on options, and you've got values for the you can put for the entry and removal. And for this example, I just picked 0.1 for entry and 0.2 for removal. I'm making so like once it's in, I don't want to take it out so easily, because if it got in, there at some point we thought that it had merit, and so I'm just going to leave it in. So let's put in 0.1 and 0.2.
So is that saying that if it's below 0.1, they will include it, if it's above 0.2,
So
they
you-
will exclude it?
Right, so if you got your current set for your model, you have two things to consider. You could take up one of the current variables out, in which case we're going to check the p-value, and if it's greater than 0.2, then it meets the threshold for removal, then that's a candidate to kick out at this turn. Any variable that's not in the model, I want to check their p-values and see, does it meet the entry p-value? Is it below 0.1? And if it is, I can enter that. So I tend to use 0.2 and 0.2. But
What about the middle?
I'm sorry?
What about in between 0.1 and 0.2?
No, these are two separate things. If a variable is not in the model and we're seeing whether to add it to the model, all we'd look at is the entry one. Is the p less than 0.1? If it's sufficiently small, the p-value, then we're going to add it to the model. If we think it has value, let's include it. The 0.2 is the removal criteria. It's already in the model. It's not significant. It's substantially not significant. So I'm thinking I don't need it in the model, so let's remove it. So it isn't a range from 0.1 to 0.2. They're two separate criteria. One for coming into a model and a separate one for kicking out of the model. Then you can run it, and what it's going to have is it's going to start showing, and there is an option on the output for it that you can set to see whether it includes all the intermediate models. I guess it must have been under statistics. I think if you, under statistics button, I think it has a place where you can say include all the intermediate models. If you do include all the intermediate models, you're going to get a lot of output. So I usually say no thank you. And then in each round, it's going to tell you what variable for that round was entered or what was removed. And it can step you through the process to see how that model gets built. So you can see each step, what happened, and you can follow through. Now, this one, what I had, it went pretty quickly. So your data is different, right? No, you're using the case. Yeah, so we should have the same data. We should have the same data. So I got Asian and heterosexual. You don't?
We have heterosexual, not Asian.
Heterosexual, not Asian. Wow. Let me just.
It may have been from recoding from one of the homeworks.
Yeah, we created Asian in one of the homeworks, but if we just use the data, we don't get it.
Yeah, I still have it from homework. So I have Asian.
You have Asian, yes, no. 0, 1 variable for Asian?
Like we made that variable in one of the homework assignments, but I didn't say.
You didn't save it. Oh, okay. So you didn't have that available right now. Oh, okay. Fine. Well, if you did, if you had kept it, then this is what hopefully you would get. But the point is, what happens, right? Each round, it considers the variables that are in the model to see if there's any that meet criteria to kick out of the model, and it looks at the pool of variables that are not yet in the model and sees if any meets the threshold for being added to the model. And it keeps working until it comes to a point where none of the variables that are in can be kicked out, and none of the variables that are out qualify for being added in. And then it stops, it runs the results for you, and tells you what the model is, and that last model is going to be the one that you want to report. That's the one. That's what you end up with. Yeah.
Well, didn't we include heterosexual?
Yeah.
But isn't that saying that we didn't include it?
No, it's included. It says here, see, by model 2, it has the letter B over there, predictors, constant, heterosexual, and Asian.
Yeah,
So the first it added the heterosexual variable, then the next round it added the Asian variable, and then it stopped.
When we start out, the only thing we have the PHQ score, and then.
Well, PHQ score was the outcome variable.
So there's, but there
You start off with no variables in the model.
So there's no variables, they're just adding.
If you, right. So if you take a forward approach, but you're still doing actual stepwise, and that's what I think it's doing in the stepwise, it's a forward approach in the sense that you start with nothing and the first thing you do is going to be build.
If we were to choose backwards, we'd be able to,
So you may get different results because you do backwards. It's going to start with all the variables in the model and start seeing which ones it should be kicked out.
so we never choose which ones to start off with, it's just either all the.
Basically, it's all or none, and then it goes from there. Yeah, Julie.
Your outcome variable has to be continuous to do this?
Well, this was a linear regression, but in logistic regression, you'll see you have the same option.
Oh.
So that has nothing to do with that. It's just a question of, so whatever regression technique is being used, that's the one it will use many, many, many times as it checks every round for which variables to kick out or which ones to add in. So every round it runs a whole bunch of regressions, a lot of regressions. You have a really big model, a big data set, and then it may take a little time to run. So then here, in this case, it had the results for each of the models. And the second one was the last one. That's what I'm interested in. Right? And the second one has, here's my constant, my coefficient for heterosexual, and my coefficient for Asian. And I've got my p-values in the model. Okay, so what we end up with is we're saying that heterosexual was significantly associated with PHQ score. And on average, heterosexuals had fewer depressive symptoms. They had a PHQ score about 4.5 lower than non-heterosexuals. The Asian students was a trend towards more depressive symptoms. But that's the whole point of the stepwise is that's one method for trying to get the number of variables down when you don't have enough observations. There's other things you can do, like with recodes. You can take categorical variables, make them dichotomous, or make them continuous if that was an option. Right, there are other ways we can also see about reducing the data. Some things people will do is run all the bivariable analyses and say, I'm only going to include variables that in the bivariable analysis the p was less than 0.2. And use that as a filter to see what gets put into the model. And then there are some more sophisticated methods. Yeah?
Besides trying to cut down on the number of variables, is there any other reason you use this? Like, let's say you have enough data, would you ever use it to try to make a better model, or would you have data to run it?
Definitely not. Like, if you can have all the variables, put them in and just run it, do it. Okay? That's our hypothesized model. That's good. Everything else we're going to do is going to be, you're not going to necessarily get the best model. You're just going to get, hopefully, a good one. But I do like these approaches when I'm trying to do a simple predictive model. Then I have less objection, let's just say, to it, because I was doing a forward regression and trying to keep it simple that way. On the other hand, you can just run the full model, see which ones seem to have any real association, use those, rerun the model, and just take that if you're trying to do a predictive model. So, and then it shows you the rest of the details, right? At each round, what were the variables that weren't included? So after put in heterosexual, this was the pool left over. Then we added in Asian, so this was the pool left over. And it's showing some of the values, and we see that the p-values here were all now greater than 0.1. So it didn't meet the criteria for entering the model. And all the p-values for the variables that were in the model were all less than 0.2, so it didn't meet the criteria for kicking out of the model, so it stopped. Okay. So again, linear versus logistic, and we're about to do logistic now, finally, right? Which one you use depends only on the outcome variable. If the outcome variable is continuous, you use linear regression. If it's dichotomous, you use logistic. Doesn't matter what the independent variables look like. So now let's understand about what logistic regression is. It's really going to essentially do a linear regression for us. The problem is when you have a dichotomous variable, it will not meet the assumptions for linear regression. Okay? It's not without being a if it's just a 0-1 variable. So that's a problem. But linear regression is a very powerful technique. We'd like to be able to use it. So we trick people, right? We say, ha, 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 I can fool this data. And it takes the dichotomous variable and it transforms it. And it says, I'm going to do some other calculations. I'm going to change things. And instead, it creates something known as a logit, or the natural log of the odds. So the odds was the p over 1 minus p, natural log. You don't have to worry about it. You're not doing that. And instead says, if I change my outcome variable and transform all the data to match it, to go along with it, then I could have a model that I could use linear regression for. I'm going to change it so now my outcome variable is no longer a 0, 1 variable. And if it becomes continuous, I can run linear regression. So it does the transformations, does its mathematical, incantations and so forth, then runs a linear regression in that transform model, and then goes back and says, let's put it back into the way the variables were originally. That's essentially what we're trying to do, or that's what we're trying to get to. So let it do whatever it wants, but eventually we want to get it back to what's the association with the outcome, with a dichotomous outcome variable. Outputs. When the logistic regression's run, it's running on that transform model. So I really don't care about what the results look like in that transform model, because I'm really interested in talking about it in the terms that I express the problem in. I express the problem in as there's a dichotomous outcome. It's a 0, 1 variable in my outcome. I want to look at how different predictors are associated with that outcome, not the transformed version. I don't really care what's associated with the logit, right? Whatever that is, right? So that we don't want. It will be in the outputs. The output we want, to untransform it, we just want to get is, instead of having a natural log of something, we want to cancel that out. Well, the way you cancel out a natural log is to take e raised to that power, because e raised to the power and natural log, right? So they're inverses, so they cancel each other out. You take a natural log of something and then do e raised to that, you're back where you started, right? They do the reverse things. So, so when we run this, we're going to say, and we're going to have to check off an option, say, I want the exponentiated coefficients. I want e raised to that. When you do that, then we are going to get something that is we call the odds ratio. And that's how we're going to interpret things in a logistic regression. If the coefficient, keep in mind, if the coefficient is 1, it now becomes e raised to the 1, or 2.71. So when you see a coefficient of 1 in the transform model, that's already really an odds ratio of 2.7. We've mentioned odds ratios before. It's been a while, but we talked about odds ratios. And it's not very intuitive. Now you're looking at the odds in one group divided by the odds for a different group. What are the odds of, that example was the odds of breast cancer in females who's had their first child after age 25 versus the odds of breast cancer in women who had their first child, at 25 or under, or 24 under. I forgot what the cutoff was. So whatever it is, right? Not quite as intuitive. But that's how it's going to be in logistic regression. We're going to have odds ratios, and we have to interpret it as odds ratios. If an odds ratio is 2, then we're saying one group has twice the odds of the outcome than the other group. It's not the same as twice as likely. So previously we talked a little bit about the difference between an odds ratio and something that's known alternatively as a risk ratio or relative risk. Risk ratio, relative risk, the same, but odds ratio is different. An odds ratio is an exaggeration of that relative risk. Whatever your relative risk is, for the same variables, if you want to look at what would be the corresponding odds ratio, that odds ratio will be further away from 1. An odds ratio or relative risk of 1 means the numerator and denominator, they have the same risks involved or the same odds. So that means there's no difference in the group, right? So no difference when the odds ratio relative risk is 1. The further you move away from 1, the bigger the effect. Your odds ratio will never be between the relative risk and 1. It's always beyond the relative risk. It may be essentially the same. It could also be quite a bit further out. So the odds ratio is going to be an exaggeration of the relative risk. When the outcome variable is uncommon, or so extremely common, because we have a variable, an event, 0, 1, depending on which one you define as 1. But I'm assuming that the less frequent event, the less frequent outcome, that's your 1, that's your event. If you're looking at mortality, you're looking at readmissions to the hospital and so forth, usually talking about things that are not the norm, the things that happen less than 50% of the time. If your outcome is a small value, like is a 2% prevalence, a 3% prevalence, something like that, then the odds ratio will be very close to the relative risk. So the odds and the actual risk will be very similar. In which case, when you run a logistic regression and you get an odds ratio, that's actually very close to the actual risk. But when you do something like, where a variable is like 20 or 30% of the population, if your outcome variable is whether amongst adults and you're looking at hypertension, right? So there's a lot of people with hypertension, and if it's something like 30% of adults or something like that, right? So if you look at different risk factors, those odds are going to be very inflated. That if you did a relative risk, you'd get much closer to 1. So you have to keep in mind when you're dealing with odds ratios, how prevalent is that outcome? Are those odds close to the real risks? Or is it actually perhaps a gross exaggeration? And running the logistic regression will see that you can also get confidence intervals for the odds ratio. And that's usually, in fact, part of the standard way we talk about the logistic regression outcomes. Anyway, so otherwise, now we're the hypothesis testing, when we do, like for all those coefficients, we're running regression, right? Then it does the t-tests and so forth. So that's being done on that transform model. So we're checking whether the transformed coefficient is 0. In terms of odds, you do e to the 0, that's 1. So it's the same thing as finding is the odds ratio 1. That would mean no difference. Okay. We're going to do it using the same data. We're going to run a logistic regression now. So let's consider a model for anxiety. So it's still using the lower classman case data. The outcome variable is going to be for the generalized anxiety disorder, do they screen positive or not? By the way, I think it's actually, because of the shorter class, some things were moved to next week. That will be when I go over what your outputs of the regressions, whether it's linear and logistic, how each of those should look in the tables for your reports. Okay, you didn't need to be doing your regressions for interim report 3, so you didn't have to have it today. So that was one of the things I pushed off so we could get started, make sure we got started on logistic regression. So our study variables, we have 4 study variables listed here. And I'm not using the one you created in homework, so hopefully we'll be okay here. Home within 50 miles, female, Greek, sorority, or actually minority. Was that maybe that was minority 01 that created in homework? So I'm not sure if you'll have it or not. We'll have to see. So we have 4 study variables, and we also have 3 adjuster variables. And so we're going to want to run that in SPSS. So now we're going to open it up, go to regression, and right, and we're going to go to analyze regression again. But instead of going linear, picking linear regression, we're going to pick binary logistic. Okay, binary logistic. Binary is a 0-1 outcome. Right. Oh darn. That's not the, 1 second, I just want to check something, because I'm seeing, this is back with Asian in it again. It's supposed, and I just, so I see, I changed the examples. So, okay. How many of you have the Asian variable from when you did it in homework, still in your data? A few do. Okay, well, if you don't, use minority, just for running it now, just try to get something there. So if you don't have Asian, do you have minority 01? No? Okay. You know, you can do also is, you have something for race ethnicity, right? So if you want, you could also do is add that variable, and you'll have a chance in a minute to tell it it's a categorical variable, and let it include it that way. So answers won't be exactly the same. But let's put in the covariates. Okay, so so you put in the variables, then the button for categorical is where, in truth, there really is should be no difference. I mean, if you have a linear regression, logistic regression, the independent variables could still be categorical. But in logistic, it gives you the option of identifying variables as categorical variables. Generally, I don't recommend using that. I tell you instead, right, to make all your 0, 1 dummy variables and choose the reference group, leave that one out and put the other 0, 1 variable, other dummy variables in the model. You have less flexibility about the reference case if you put it in as a covariate. So you put it in as a covariate, and you just put it in and define it to be categorical. You can have an option to pick the first or the last as a reference group, but you couldn't pick something in between, I think. So, you know, you'd be a little restrictive. Usually it's like, let's explicitly cover what we want there. But if you need to do it for right now for the problem because you don't have Asian separately, you know, that's fine. So once you put in the variables for the covariates, which is, those covariates, that's all your study and adjuster variables, right? In the linear regression, it called it independent variables. They're still independent variables, okay? Here, but they call it covariates here. So if you click on categorical, that's where you can say, one of these variables, tell it it's a categorical variable. I don't really have any because everything's that would have been has already been converted to 0, 1 variables. So I don't really have to worry about it. But if you're doing it within a categorical variable, you just take the variable, send it over to be categorical, and then for that variable, it's going to ask you to, what to do here. You know, it's an indicator variable, but the reference category you can pick to be the first or the last.
What if you try to run regression and don't do this step? You have a categorical variable.
Right. So if you don't, if you include, say, the categorical variable without telling it it's categorical, then your categorical variable may have been coded, let's say, as 1, 2, 3, 4. It's going to consider that a continuous variable. 1, 2. It's going to be a scale variable. 1, 2, 3, 4, and it will treat it with those values, which means the second group is one more than the first group. Some cases, you're dealing with something ordinal, and that's not unreasonable. Other cases, like physician specialty, there is no concept, there's no scale involved here. There's no order to it at all, right? Though some of them may feel differently about it. So they're really just different categories, different buckets. So
So does it essentially make like temporary dummy variables to run it?
yes. So if you don't do the dummy variables, it will. But in choosing the reference group, you're restricted. It's going to only allow you to tell it whether it's the first or the last. Like I said, I just go always do all the recodings, make all the dummy variables. I do all of that in the beginning, get that done, and then work from there.
What's the difference between listing the reference group as first or last? When it comes to that?
It just means which one will it consider the reference group.
Oh.
That means if it's the reference group, right, it's not in the model. All the other ones are in. So it's just deciding which one it's going to leave out of the model when it runs it.
Oh, okay.
But remember, all those interpretations are done relative to the reference group. So you'd like the reference group to be chosen with thought. Maybe your thought will be it's the first or last level, but that's all you'd be able to do there. But then you have to do it every time. You have to make sure you define it every time you run it as which is the one is the reference group. So like I just create the dummy variables. It doesn't take very long, and then just go from there. Now, if you click on options, it's very important when you run a logistic regression. You do need to click on options because there's things you want in there. If you don't click on options, it's not going to do the e raised to that transform coefficient, and so you won't get the odds ratios for you. You'd have to compute them yourself. So we want it. So when we get here, we do want to click on, oh, actually, no, wait a second. No, maybe it does include it. It just doesn't do the confidence intervals. Okay. Okay, because they move between different software packages, they sometimes get them mixed up. So it's the confidence intervals that wouldn't get created for those transform coefficients if you don't tell it to. In linear regression, the standard it seems to be that when we give the regression coefficient and the p-value in your outcomes, but whether or not to include the confidence interval for the coefficient is optional. In logistic regression, the norm is provide the point estimate, of course, the odds ratio, okay, and the confidence interval, and the p-value is optional. So it's become the conventions. Not that it's uncommon to provide both the confidence interval and the p-value, but there's like the minimum that you do is different for the two cases.
What's the classification plots? Because that wasn't checked off.
Yeah, I don't bother with that. I don't think it's really worth anything. Yeah. Well, it gets into if you want to use your model for prediction, and you can set the level is you predict the event happens if the probability is greater than 50%, and then it sees how you did against that. I don't generally find myself in such a situation that that's relevant, so I just never use it. I don't think it's incredibly useful, but I guess if you're going to usually for prediction and say everybody, if you have a 50% chance of it happening, then you get predicted to have it. You can see how you do. Most of the things you do in health, we don't do so well that way. We're dealing often with predicting events that aren't super common, aren't going to ever be. Almost never, very few people would have greater than 50% risk. If you're looking at risks of major cardiovascular events, right, or certain cancers, you tend not to have people who have greater than 50% risks. So like you'll predict 0 for everybody. You predict that it wouldn't happen for any individual. You're really only looking at it as a group, what the prevalence, what the incidence would be as a group. So definitely want to check off the confidence interval for the odds ratio. And then when you run it, it gives you a couple things along the way, like what's included in the analysis, and it tells you, this part is saying the original value, that's the way the variable is. The variable had the values in your outcome 0 and 1. Internal value means that's the values it uses when doing the analysis. If your variable was coded, hard-coded to be 0, 1, this is what you get. But if you had a variable where you didn't code a 0, 1, and you had to tell it which is the 0, which is the event category, which one isn't, then it could be the original values might have been 1 and 2, and it got converted to 1 and 0 or something. So you have to look at it. The reason why you look at it is the odds you get are the odds of a 1 for your outcome variable. You want to make sure what it considers a 1 in doing the analysis is the same as what you considered to be the 1. So I have had cases like I had a student met with recently, and the odds ratios she was getting were all going the wrong way. Things that people who were supposed to be at higher risk seemed to have lower risk. And the reason was the way it was originally coded, and she specified things for the outcome variable, because if it's as categorical, she had it swapped. Which was the 0 event, which was the 1 event. So instead of getting the odds of the event, she got the odds of not having the event. Always a good thing to check. So if you look at here, you can confirm that it's doing things the way it's supposed to. The other thing to do is look at those odds ratios. Make sure it makes sense. Does it pass the sniff test? Does it seem like things that you know should definitely go in a certain direction? Is that what's happening? Things that should be higher risk, are the odds greater than 1? Things that should be protective, the odds ratio should be less than 1. Take a look. Make sure that you've got it coded right. Then some other information, what's in the equation, what's not in the equation. You could have run it stepwise again. We just, leaving it, we're running with the enter, we're just running everything in it. We can just kind of continue on. Classification table, again, I don't necessarily find those things incredibly helpful. Now we get to, here's the key part of the output. And again, yours, because of the way you did it, if you didn't have the Asian variable, it's going to be a little bit different. So let's, hopefully it's not going to be wildly different for the other variables like gender, heterosexual, and Greek, and so forth. So, but let's look to try to interpret it here. First thing, which is the column with the odds ratios? Barbara. What's the heading of the column with the odds ratios? Right. Yep, exp parentheses b, the third from the right. Right? That means exponent e raised to b, the coefficient in the transform model. So we don't really care what's happening on the left side. We really only care about the right 4 columns. That's going to give us the p-value, the odds ratio, and the confidence interval for the odds ratio. So the right 4 columns is all we want. Making sure that, again, that when it had those options before, we checked off that for the statistics, we wanted to see the confidence intervals for the exponentiated coefficients. So if we look over here, let's take a look at the variable, well, let's just use the one for Asian. You just look up here then, right? And let's see about interpreting that. So who would like to take a stab at interpreting that? No volunteers? Okay. Adam, you feel brave?
No.
That was emphatic. Maureen, how are you feeling? You willing to take a risk?
That Asians have an odds ratio of 4.135 times that of other.
So their odds are 4.135 times the odds of non-Asians, of the other students. I think what ended up happening, it was mostly white and Asians. Caucasian and Asians was basically it. So almost everybody. There were a very small number of the others. But so right, and is that a statistically significant odds ratio? Maureen? What's the p-value for it?
0.001.
Right, 0.001. So is that statistically significant? Well, what would be the rule? What would you use to be significant?
Between 0.01 and 0.05.
Less than 0.05. Right, so is it less than 0.05? Yes, okay. So it's statistically significant. So we say that it is a statistically significant association. Asians had much greater odds of being, having generalized anxiety disorder, a positive screen. And the confidence interval for the odds ratio is 1.769 to 9.668. Yes, Rachel?
So when you ran it, because I didn't have the Asian recode, I just had all the races categorically.
Okay.
Is my odds ratio different for the category that lines up with Asian because it's comparing it to? is it
Well,
not-
actually, which one is the reference group?
I chose the first one.
We'll see what's in the model.
Well, it's only listed as race 1, 2, 3, 4, 5, so I don't really know what that means.
Okay. Right, so if you didn't get the descriptives run, it would be hard to figure it out. Otherwise, you get descriptives and you'd get the frequencies and all those groups and you could see which one it is. But yes, you had to compare it to something.
But it's only
It's only going to appear to the reference group.
A different value.
So it's hard if, I'm not sure what if the reference group was Caucasian, you'd probably be fairly close. What did you get for your odds ratio?
I'm not sure.
For Asian?
I'm not sure which one's Asian.
Oh, because it's only, all of them are only numbered. It didn't get the values to change the labeling. Okay. Yeah, I'm not sure. If I saw the ends in the descriptives, I could tell you. But we don't. If we didn't check off to run descriptive statistics, then I don't know.
If a significant p-value, your confidence interval won't include 1.
Okay. So the question is, if the p-value is less than 0.05, then the confidence interval, right, should, in theory, not include 1. In linear regression, the question was, is the coefficient 0? 0 was no effect. With odds ratios, 1 is no association, right? 1 is going to be the no effect. So we want to see, is 1 in the confidence interval? One catch is, it also depends on the statistical package and what options, but the calculation of the p-value and the calculation of the odds ratios are sometimes slightly different algorithms. And so occasionally you can hit a situation where they're not consistent. And one of them says one thing, and the other one says it's significant, and the other one says it's not significant. Though if it's not going to be, it's going to happen, you figure it's going to be really, really close, in which case they're really both borderline significant. And that would be the way to describe it.
So sorry, just to reiterate, if the confidence interval includes 1 in this case, then we're going to say that it's not statistically significant?
Right.
Okay.
Yes. And the standard with reporting results from logistic regression is give the odds ratio and the confidence interval. Sometimes they give p-values, sometimes not. So usually, but you're always going to get the confidence interval. So, Rana.
Statistically significant, the p-value is 0.001, but it does not include 1 in the confidence interval.
Exactly.
So it's
No, it's not opposite. We're saying if it's significant, it shouldn't include 1. It should not include 1. An odds ratio of 1 means no association. So if 1 is not in the ratio, is not in the confidence interval, we're saying we're not considering the 1, the no association is not considered reasonable. Only the values in the confidence interval are considered reasonable. So we can see, if you look up and down, you'll find, and then when you see the 0.053, the one that just missed, you'll also see the confidence interval went from 0.21 to 1.01, right? It just covered 1. That's consistent, right, with what the p-value is telling us. Okay? Great. For heterosexual students here, and again, you did it, your model was different. Rachel, what did you get for the odds ratio for heterosexual? 0.135. So that's what I was expecting, you'd get something very, very close. So here I have 0.144. So we're saying there is that the odds of a positive screen for generalized anxiety disorder was only for heterosexual was only 0.144, only like 14% what it was for non-heterosexuals. Another way of looking at it, which makes it a little easier for interpretation of these things, is to look at it as percent more likely, or percent greater, or percent less. So we have a few here. So for the gender effect, so the females, right, had an odds of, that should be anxiety, I think, right? Wasn't this anxiety, this one? Or was this depression? Oh, it was PHQ-9? Okay, I'm sorry. In the table we gave before is an example of counting up the variables. I had anxiety disorder, and that's, I'm sorry. So in terms of the odds of depression, we said the females have an odds 0.46 that of males. That means only 46% that of males, or you can do it as subtract it from 1 and say it's 54% lower odds. Okay? So the odds of depression in that group, it said for the women, were 54% lower than for the men. Going up here, for the heterosexual, the odds of depression in the heterosexuals was about 86% lower than it was for the non-heterosexuals. Okay? If the odds ratio for the 4.135, well, that's really big. But if the odds ratio was 1.5, then we'd say the odds are 50% greater in that group than the comparison group. Yeah, Katie.
How do you know that it was females who had 0.46 as opposed to?
Yeah, you have to see how gender was coded. If whatever is the one variable, that's the one you're interpreting relative to the 0 value. That's why I usually recode things, especially gender. I hate that, because then it's like I'm always forgetting, and everybody codes it different, which one is male and which one's female, right? So you never know what you have. So I always try to recode it and make sure the name of the variable expresses the characteristic that is associated with the score of 1. So so if 1 was female, I'd just make a new variable whose name was female, and 1 for the females, 0 for the males. So I don't really care whether you make it female or male, but just make sure it's clear. However, in interpretation, you may have a preference. If you know that one sex tends to be at greater or lower risk, or that's the one you're trying to see how much additional risk this one group has, then you may choose to make that the one. So if you're trying to say that we think women are at greater risk for something, then have the variable called female so that we express the results in the greater risk of the females relative to the males. So in terms of overfitting, so we talked today already